Section 4.3, Separable Equations. Now, the separable equations just means differential equation, just means that your differential equation can be written like this. That is, you have y prime on one side, right? And then the equation itself can be split up into two functions multiplied together, f of x times g of y. Now, some of the examples, as you can see here, include something that you might imagine: x squared minus 4 times 3y plus 2 on one side, and the other side has nothing but the derivative of y. However, it can also be just with x or just with y, or some mixture of the two. Is the bottom separable? Maybe. I don't know if the bottom one is even separable. Doesn't matter. But the point is, the separable ones are the ones that you can factor them into individual functions that include only x and only y. Now, the ones that include only y are called autonomous differential equation. And that is just a cute name, okay? And we don't care what it's called. And anyway, so to handle this kind of differential equation is easier because they are separable. What happens then is we can break them into two parts and then integrate both sides and hope that something will come out. Now, to do that, let's look at example 4.10. So example 4.10 says that y prime, which is dy by dx, equals to x squared minus 4 times 3y plus 2. And then we are going to do a standard trick. Being that it is separable, we're going to isolate the y on one side with all the other y's, especially under dy. So that's 3y plus 2. And then the x on the other side too. So that is equal to x squared minus 4 times dx. And then we're gonna, now being that they are each individual integrals, then we draw the integration sign right here and then integrate this thing individually. So that then, in other words, we're gonna do two integrals at the same time, and each with its own variable. So this side, we're gonna integrate this thing that's equal to the natural log, okay, 3y plus 2, and then you have to adjust the 3 by dividing by 1/3. Dividing by 3. And then this side, then we have the power rule, x3 over 3 minus 4x, and then plus a constant. There's actually a constant here too, but we don't need two constants. One's enough, okay? So we have the constant here. And then we have, let's see. Why this? So continuing, we'll move the 1/3 over here. So we have the natural log of 3y plus 2 equals to x cubed minus 12x plus a different c. Okay, we'll just call it c1. c1 is just c times 3. But being that we don't care what c is, we'll just call it c1. And then next, c can be anything, right? So any number. So then continuing, we need to take the y out of there by applying the inverse function of natural log, which is the e. So we stick a giant e down here, like this, okay? E of this whole thing, including the constant. So that gives us 3y plus 2 equals to e to the x cubed minus 12x, and then the c1, that the c1 is the same as e to the power c1, so we'll call that c2 and put it down here. And this is still in absolute value, but so then continuing, digging it out of there, so we have 3y plus 2 equals to plus or minus c2 e to the x cubed minus 12x. And finally, we'll take the y out of here, which means y equals to plus or minus c2 e to the x cubed minus 12x all this stuff. We're going to subtract 2, 12x, subtract 2, okay, and then all divided by 3. And that should be the answer. Now let's check. Now the only difference is we have a plus minus C2 here, but being that we don't know what that number is, we don't care what it is really. So then it can be just, well, anything. So we'll just replace this thing and call it C. So this thing will be called C, okay? And that should be good enough. And also, your book does mention that C2 is actually positive because it's the e to the power of something. Which is fine, which is why the plus or minus sign can be replaced. Otherwise, if C2, well, anyway, it basically can be anything, okay? Because the derivative of this thing will eventually end up, well, this equation should eventually fit in here and solve the original differential equation. For this value of y. For really any value c, that should work out. So that's that. Next. Now, next example, we're going to do a very similar problem, except that this time there's an initial condition there, where that is where x is 0, then y equals to a set value initially, which is in this case -3. So you're going to do the problem exactly like this, with one more step. That is, you're going to eventually solve for c, where if x is 0, y is some other value, some kind of set value, and then that will allow you to solve for c. In this particular example, you're going to have to integrate y squared minus 4, as you can see down there. And to do that, you have to break it into fractions. The partial fraction decomposition, which remember we do have a partial fraction calculator for the purpose. So please do example 4.11 as your homework. Well, notice that example 11, the integration is not necessarily that hard once you break the fraction apart. But once you have finished the integration, you are left with doing a ton of algebra. You know, as you notice there, because you have y on both the top and the bottom of the fraction, see on top there, and then you have to somehow get that to come out. So a ton of algebra is still just algebra. So if you patiently get through this stuff, you know, eventually you will get to the end if you don't make a mistake among all that mess. So that takes a bit of patience, and but please do that anyway, because it's very, very good practice. So next, let's look at the next problem, which is example 4.12. We're looking at salt tanks. Example 4.12, the salt tank problem, is that we have a tank. It has 100 liters of salt solution in there, and we have salt solution going in at 2 liters per minute and coming out at the same rate. So the 100 liters stays even. And then the amount of salt going in is has a concentration of 0.5 kilograms per liter, and the one going out, we don't know. We got to figure that out. And so we will use the U of t to represent the total amount of salt at any given time in the tank. So we're given, however, when time is 0, the amount of salt is 4 kilograms in the tank. So with that amount of information, we will figure something out. Like what do they want? They want to know that find the amount of salt as a function of time. Okay, so we'll figure out how much salt there is and at any given time. Okay, we need to come up with the equation for it. So then, so how are we going to do that? So the differential equation we are going to use is that the rate of change of how is this changing? The rate of change, which is du by dt, okay, that is changing by increasing the salt intake. Okay, so the change is that it's gaining 0.5 kilogram per liter at the rate of 2 liter per minute. So we'll take 0.5, okay, kg times 2 liter, 2 liter per minute. That's that's per liter, right? Kg per liter. So then per minute is getting into the rate of change is adding 0.5 kilogram times 2 liter per minute, which, okay, that's the end, that's the going in. Now, but that's, what about going out? It's going out by the same formula. That is, it's subtracted by, that's the addition, that's subtracted by when it goes out, a certain amount of concentration, okay, also times 2 liter per minute, 2L per, let's see, yeah, 2 liter per minute. Per minute. Okay, so then, so the inside is, well, given as 0.5 kilogram. What's the concentration going out? It doesn't give us, but we know that it is equal to the total salt at the time, whenever that is, divided by the volume of the tank, which is 100 liters. And at that rate, with that, that will give us the concentration of the tank at any given time, assuming the tank is being stirred properly. So then the concentration coming out is exactly the total amount of salt divided by the 100 liters. Now with that, we have, as you can see, if we rewrite this without all the units, we have 0.5 is 1, times 2 is 1, minus u over u divided by 50. Okay, u of t divided by 50. That is du by dt. And that is the differential equation that we're supposed to solve. Now, once you solve this differential equation, this is an autonomous differential equation, which means that there is no t on this side. So you push all this thing down here, move the other t over there, like this, right? So you have, let's see, I'll write it down here. So du equals to 1 minus u over 50 times dt, and then you integrate both sides. And so this becomes a natural log situation. And by the time you work everything out quickly, then you come up with some kind of a solution. Right. Where, and once you come up with a solution, then plugging in the u equal to 0 will give you the, will solve some kind of, solve the problem. So the solution for this integration is ut equals to 50 minus c1e, etc. Okay, that is your solution if you get everything right and not mess up. And then eventually you will figure out that c1 equals to some set number. Well, by plugging in the initial value, see, because u0 is 4, right? Because the initial u0 is given as 4, and so we have, so then you quickly calculate what the c is, and yeah, and that's about it. That is your equation. We also want to know what happens when t goes to infinity. That is, as time goes on, does the tank's salt solution approach some kind of equilibrium? And in this case, it does, because the answer is some kind of e to the negative t. So as t approach infinity, then that value goes to 0. So the answer is 50. So eventually the tank will settle down into a amount of having 50 u of t. That I believe is 50 kilograms. All right. It will, right. So that's that. With that, please finish this example as part of your homework. This is example 4.12, as well as the following problem, which is the cooling of pizzas, which goes almost identically to this, not this one, almost identically to this one. Okay, and then you do some kind of integration that end up being the natural log, and then you plug all the information in, and out pops your answer. So please do example 4. What is this one again? 4.12 and 4.13 as your homework. Now for homework on page 391, please do problems, let's see, 119, 121. 121 has a small error, as I note in the video description underneath. There's a small error. It should read minus y plus 1 instead of just y plus 1. And so next, problem 125, 131, 33, 39, 41, 45, 51, and 57. Problem 157, I believe the answer in the book in the back is wrong, and I will talk about it later. Explain why I think so. And lastly, 167. So please go do your homework, and in the next video, I want to talk about the homework after you're done with it. Now, solving the differential equations, the separable differential equation, might look like there's a ton of algebra, which it does sometimes, so please do it patiently. However, at least in this homework, in this section, there's not actually that much algebra in it. The problems are fairly straightforward, most of them. So, so please do your homework, and I'll talk about it later.